And you won't need much physics, although there will be some physical terms creeping in from time to time. Basically, I was always interested in algebraic graph theory. And at some point in my career, some lost physicists end up in my office with graph theory questions. And so I started working on some of these problems that are arising from quantum physics and quantum computing. Now, the subject has grown a lot, and so I'm going to give you sort of a random sample of what things that are going on. It's by no means complete, and it's not even particularly representative. So I'm breaking up the talk into three parts. I can talk about walks, lines, and colorings. And so there's walks. And so the subject I'm bringing up, we come under the heading of a continuous quantum walk, but you can forget that for the moment. So the understanding is I'm given a graph X, and a graph's got an adjacency matrix, which I'll denote by A. And the physicist will define what we call a transition matrix, which is the exponential of ITA. So you can define that by the power series. There's no particular problem, it's well defined. We always denote it by U of T, and that's standard. And the U of T is a unitary matrix, and it's also symmetric, which is a little unusual. You don't expect a unitary matrix to be symmetric, but this is. And to give a very simple but useful example, we just take the complete graph on two vertices K2, and you work out the series. Now, in this case, you get a power series, but the trick here is that any even power of A is the identity, and so you get a simple formula. And you see, as I said, that's symmetric, and if you checked it, it's also unitary. So this family of unitary matrices is describing what the physicists would call a continuous quantum walk. And occasionally people will say that these are analogous to the classical random walks on graphs. And they may be in a very vague sense, but I've never found that I've never seen any examples of where a physicist got useful intuition by looking at it that way, let's put it that way. So we have this object that the physicists are interested in. Now, of course, they've got some questions about these things they want to answer, so I need to explain what those are. So U of T is a transition matrix. It's describing the evolution of some d-dimensional quantum system, okay? Or controlling the evolution of a d-dimensional quantum system. So the system is d-dimensional. It starts, we'll assume it starts in some state, and we will run our U of T for some time, and now it's in another state. And we're asking questions about what happens, how things change. So to make sense of that, I need to say what a state is. And I'm going to take the view, and this is completely standard, this is what you would see in the first course in quantum mechanics necessarily. The state is given by a d by d matrix, and it's quasi-semi-definite, and its trace is 1. So now you can ask what states mean, and then you get yourself in all sorts of problems, and then you start worrying about poor Schrodinger's pussy and things like that, but we don't need to worry about that. The state is just going to be a density matrix, quasi-semi-definite, trace 1. And the density matrices we see a lot of the time will just be built from the standard basis vectors. So in fact, I'm going to define D sub R to be the product E sub R transpose, where E sub R is the R standard basis vector. So that's a D by D diagonal matrix. The R entry is 1, and all other entries are 0. And I'll probably call this a vertex state. And so the understanding now is that we have an initial state. We let the system evolve under U of T for some time, and then we have the current state. Now, the state at the time T is given by the product U of T, D, U of minus T. Now, at this point, you could forget most of the physics, provided it's going to motivate your choice of states and things like this. But the point is, we've got U of T, which is defined using our graph A. And what we've defined now is a so-called continuous quantum walk. Okay, there are also discrete walks, which are in some sense hard to deal with, and in some sense more useful. But this defines a continuous walk. So you're going to be asking questions about this matrix D of T at different times. Now, the first question I'm going to discuss, and the one that one of the more important ones, is called perfect state transfer. Now, one of the problems with quantum computers is a, we can think of a quantum computer as a collection of qubits, two-dimensional complex spaces. That's all well and good. If you're running a computer, at some point it may occur to you, I want to copy the states of some of these, or one of these qubits. And the state of a qubit would be could be viewed as a unit vector in a two-dimensional complex space, but you'd like to copy the state. And well, it follows fairly quickly from the axioms of quantum mechanics that you can't copy states. Okay, but you can use continuous quantum walks to get around this limitation, and that's what I'm going to explain next. So the jargon is we have perfect state transfer from a vertex R to a vertex S, or from the density matrix D sub R to D sub S at time t, simply if D sub S is D sub R at t. So D sub S is U of t, D sub R, U of minus t. Okay, so that's the definition of state transfer. So now we've specified the initial state and the target state. Okay, so we're in a very concrete situation. If we look at K2 again and do the little calculation, you discover that time pi on 2, U is equal to 0I, I0. And when you do your calculation, U pi on 2, D1, U minus pi on 2, you get D2. So the interpretation of this is that at time pi on 2, you've got transfer from the state D1 to the state D2. Now, if you're working with a network modeled by the graph that gave me my adjacency matrix A, okay, then this is telling you that, the first vertex is in a certain state at time 0, then at time pi on 2, the vertex 2 will be in exactly that state. So functionally, it looks like copying. The problem is that there's a delay involved. Okay, you have to wait for time pi on 2. But so perfect state transfer, I've told you what it is. We're going from one vertex state to another. It's useful because it enables us to get around a limitation on copying states. So now, this is not the only possible sort of transfer between states. There's a second class of problems, which I'll talk about too. So this comes on the heading of uniform mixing. Now, I can always go into it straight. So I'm going to call a complex matrix flat if all its entries have the same absolute value. And these days, if you have a flat unitary matrix would often be referred to as a complex Hadamard matrix. In the old days, that term had a slightly more restricted meaning, but so a flat unitary matrix is what would often be called a complex Hadamard matrix. And the jargon is that we have our continuous quantum walk shows uniform mixing at time t if the transition matrix U of t is flat. Now you see why I picked K2 as my example, because when you calculate the transition matrix of K2 at time pi on 4, you get 1 on root 2 times a matrix with entries 1 and I, and so the absolute values of the entries of that matrix are all 1, so that is a flat matrix. So it does happen. Okay. A somewhat more exciting example is to look at the D cube. Now the D cube is the Cartesian product of copies of K2, and it turns out that the transition matrix will then be the Kronecker power of the transition matrix of the factor. You don't think you're raising the power. So for the D cube at time pi on 4, the transition matrix is a Kronecker power of the matrix you get from U of K2 at time pi on 4. And you see straight away that is flat. So that is another, so we have uniform mixing on the D cube. You can also use this argument to show that you get perfect state transfer between the antipodal vertices on the D cube. Okay, so it does happen. I mean, it's a little bit harder to find a justification for uniform mixing. I mean, it's giving you a sort of completely random output. But then in cryptography, for example, there are times when you do want a completely random output. And it turns out to be a mathematically interesting question, which is enough justification for me anyway. So what are some examples of uniform mixing? Well, the complete graphs on 3 and 4 vertices show uniform mixing. The Hamming graphs, which I'm not going to define, so Q equals 2, 3, and 4 have uniform mixing. And Cartesian products of graphs with the same mixing time have uniform mixing. So if you take Cartesian powers of K3, that graph will have uniform mixing. So you do have infinite families of examples. On the other hand, there are lots of things where you might expect to get uniform mixing in general. You don't get uniform mixing. There's no uniform mixing on an even cycle of length on more than six or more vertices. If these are prime greater than 3, you do not get uniform mixing on that cycle. And you don't get uniform mixing on the complete graph, Kn, if n is bigger than 5. Now, that last fact is fairly easy to prove because for, well, I'll show you the technology in a moment, but we can actually compute U of t explicitly and easily for Kn, and we can see by inspection essentially that we don't get uniform mixing, which is a bit surprising because if you think of a random walk on a complete graph, it's going to mix as fast as anything. But in the complex case, you do not get uniform mixing. I won't go into that. And so the state, the question which sort of concerns us is simply which odd cycles do admit uniform mixing. This is an open question. C5 does not, although that's not trivial. The first open case is the 9 cycle. Every time one of my friends says they've proved that there's no uniform mixing on 9 cycle, then a week later that gets withdrawn. And so 15, nobody has a clue about, for example. So we do not know which odd cycles admit uniform mixing. That's a nice, simply stated open problem. The question is, how do I work with these things? The tool we use most often, I define the U of t in terms of the power series, but obviously I'm not going to work with that unless I'm using K2. So the trick is to use spectral decomposition. Now, if I have an adjacency matrix, it's symmetric, and so I can expand it as a sum theta r e sub r, where theta sub r runs over the distinct eigenvalues of A, and E sub r is the projection onto the corresponding eigenspace. So that's the spectral decomposition of A. Now, it's useful in many ways, and so particularly you can read off the spectral decomposition for U of t. That's x per ta, so you just apply x per t to the eigenvalues, and you get that U of t is equal to the sigma e to the I t theta r times E sub r. So we have the spectral decomposition for U of t. Okay, now the point is that if I have A, then I can work out the idempotence. I can do it in Sage or Mathematica or whatever. Okay, and we can work out the eigenvalues. So this is useful both theoretically and to do calculations to try and see what's happening. Now we go a step further. So what about, we're looking at continuous walk. We started with a state D, and then we look at U of t, D, U of minus t. And you play a little bit. Now, the important thing here is that E sub r times E sub s is 0 if r is not equal to s. And so things simplify a little bit, and you get that D of t is equal to that sum here. The E to the I t theta r minus theta s applied to E sub r d E sub x. Now, it's somewhat surprising, but you can read off quite a lot from this, because let's think about the case of perfect state transfer. In that case, the left-hand side there, the U of t, the U of minus t is just D2. So diagonal or DR, DS, say, diagonal with a 1 in the SS position, 0 everywhere else. So it's a real symmetric matrix. On the right-hand side, well, D is real, and the idempotents are real because they're built from the eigenvectors of A, and that's real and symmetric. So the matrices and the sum on the right are all real. And so as a consequence, that says that the eigenvalues, the E to the IT, what are we going to call them, the E to the IT, theta r minus theta s must be real. And that has strong consequences, which I'm not going to go into now. But so in particular, it means, for example, that sine of t times theta r minus theta s is 0. So t times theta r minus theta s is a multiple of pi. And t times theta k minus theta l is a multiple of pi. And so theta r minus theta s over theta k minus theta l is going to be rational. Now, since the eigenvalues of graph are algebraic integers, you can use that to show, get a very strong restriction on the eigenvalues of the graph when perfect state transfer occurs. So basically, they have to be the form, well, I'll approximate a bit, a plus b root delta, where delta is a square free integer. So and so in many cases, you can show that the eigenvalues are forced to be integers. So you get a very strong condition. And this enables you to make some progress. So it's bad news. It says that perfect state transfer is actually hard to come across. I proved there are only finitely many connected graphs with maximum bouncy k on which perfect state transfer occurs. Okay, and so for example, this be lazy and take k to be 2. You're looking at paths, and so this tells you that there's only finitely many paths on which you get perfect state transfer. And in fact, the only paths that admit perfect state transfer are the path on 2 vertices, as we've already seen, and the path on 3 vertices. And I also proved that there are only finitely many connected biproduct graphs on which uniform mixing occurs. We know less about uniform mixing than we do about the state transfer, but so that's why I've got to put in the word bipartite in there, for example. So that's the and there's a related question here. A problem which has been annoying us for years and years is there a tree with more than 4 vertices on which perfect state transfer occurs? We suspect not, that it's wide open, and that's something we've solved a lot of problems over the years, but this one's just sat there like a toad on a rock. Okay, so that's all I'm going to say about walks. As I said, I was talking about continuous walks. There are also discrete walks that we've worked on, but I won't go into that at all. And so I was going to talk on something related to lines. Now, I was thinking about talking about Lagrange lines, but I decided Gary could do just as good a job as I could there. So I'm going to talk about Nietzschean bias bases. Now, for that, I do drag in a bit more physics. So I talked about states, density matrices, positive matrices in trace 1. And I talked about the transitions. So you have a state. If it's going to evolve, it has to evolve by unitary operation. This is a consequence of the axioms of quantum mechanics. Although I was very amused to see in a physical quantity the statement that the axioms of quantum mechanics are not as strict as those of mathematics. If you can work out what that means, I don't know. Anyway, so we have states, we have evolution, transition, but the third part of quantum mechanics, of course, is measurement. And I'm going to take a very simplified approach to this. So we have a state. The idea is we carry out at a certain time, time t, we carry out a measurement. Now, if we measure a d-dimensional system, there are going to be d possible outcomes. Now, the actual outcomes will depend on the measurement you choose to carry out. But once you've decided, this is the measurement I'm going to use, there are only d possible outcomes. And so the output of the system is, for all practical purposes, just one of the numbers from 1 to d. So you can sort of think of it as a world's most complicated random number generator or something. So you run your system for time t, you carry out a measurement, and what you observe is effectively a number between 1 up to d. It tells you which particular event occurred. So but as mathematicians, we ignore all that. We just say, okay, we're just getting a number out. So okay, so that's what happens. Now, of course, the saying is the essence of madness is doing the same thing and expecting it to get different behavior. But quantum physics works exactly like that. If you carry out the same measurement a second time, you would not get the same result. What you're observing is a probability distribution. So if you've observed a 3 on the first trial, on the next trial, you might get a 5. If you continue, you'll get a probability distribution. And so you will know, or have a good estimate of the probability that you'll observe 3 when you carry out your measurement at time t, given your initial state. So the actions of quantum mechanics actually tell you what the probability is going to be. They tell you if the system at time of measurement is in state d, and then you observe the outcome with probability. And I've written 3 different expressions for it. The inner product of d with the outer product xi starred, or the trace of d times xi starred, or just xi starred d xi. And if those 3 things are equal, since d is positively definite, xi starred d xi is non-negative. And it's easy to check that if you sum over I, you get 1. Okay, so we do have a probability distribution on the possible outcomes. Now, so the point now is that the measurement is being specified by a north-normal basis. And in quantum computing, this is more or less the only measurement they use. There are other situations where you may have more sophisticated situations, but this is all they use in quantum computing. So we have the measurement, we have the probabilities. And so the other comment I make is if you're lazy and change your orthonormal basis to be the standard basis, then you'd have, then you'd be computing E sub I transpose D. E sub I, that's just the II entry of D. And so the probabilities are given by the diagonal entries of the current state, D of T. Okay, and since it's positive semi-definite, those diagonal entries are non-negative, and since it's going to be a density matrix, they're going to come to 1. So that's all I'm going to say about measurement. So the point is, since the measurement is specified by an orthonormal basis, and so it's natural to present your orthonormal basis as the columns of a unitary matrix. In particular, the order of the basis matters. So they're really working with an ordered basis. And so the measurement is determined for our purposes by giving a D by D unitary matrix. Its columns are orthogonal, so we're good. So now we have density matrices, evolution by U of T, and then measurement by using a basis. And as I said, in quantum computing, most of the time they're measuring with respect to the standard basis, E1 through ED. Now, I wanted to talk about these mutually unbiased bases. So the idea is that you carry out a measurement, you pick out one sort of measurement, you get a certain probability, you get some information about the state. Suppose you wanted to set up a different experiment, use different measurements, you get some more information about the state. And so then the question is, how should I choose the second measurement given I've chosen the first measurement? And the claim is that in a certain sense, to get the most information possible, if you're using more than one measurement, more than one unitary matrix, that the matrices you choose should be pairwise mutually unbiased. So you don't really, and so the definition of mutually unbiased is simply that U1 and U2 are mutually unbiased if U1 starred, U2 is flat. Now notice that U1 is unitary, so U1 starred is unitary, and U2 is unitary, so that product is unitary. And so the product will be a flat unitary matrix. But you don't need to impose unitary as a condition, you'll get that for free, but you do need to impose want to be flat. And here is an example of a set of 3 bases in C2 that are pairwise mutually unbiased. Okay. Now, it's actually easy to convince yourself that if you take a flat unitary matrix and the identity matrix, they're mutually unbiased. So in fact, you can always arrange to have the identity matrix as one of the, if you've got a pair of mutually unbiased bases, you can make a change of basis and change one of them into the identity, and then the other one's flat. So there are 3 matrices there, and since the identity is in there, the second and third matrices are both flat. Okay, and so now mutually unbiased bases have got a very large literature, and they're used in all sorts of protocols. So they're actually, they play a big role. And so what else? Questions about what are we trying to do? Well, the first thing is to think about a construction. And the point I want to make here is that simply that the construction is quite combinatorial or geometric, depending on your viewpoint. So I'm going to start by constructing, an instance matrix, really. So I'm going to pick a field F of order Q, and I'm going to look at pairs X comma Y from F. I'm going to call those points, and pairs square brackets A comma B of elements of F and call those lines. And then I want to define an adjacency relation, if you like, that XY is incident with AB if Y is equal to AX plus B. Now, that star is just multiplication, but I might fiddle with that later on. So that's just your high school algebra. So it just says that the point XY lies on the line with slope A hitting it and starting at B. So that gives me an instance matrix. Now, the saving some details, that matrix lies in the group algebra of an abelian group of order Q squared. That is not entirely trivial, but actually it's not trivial at all. But anyway, it does lie in the group algebra of abelian group of order Q squared. And there are other abelian groups so it has characters, and the restriction of the characters to the lines incident with a given point give me a bunch of vectors of length Q. So despite what I wrote there, I've got a C to D, I get Q mutually unbiased bases in C to the Q, not C to the D. Now, as it happens, the bases, I get a flat, and so I can always add the identity, and I actually get Q plus 1. So that is a construction, and all constructions of mixed unbiased bases involve some essentially some geometry. I can also present this in terms of typical distance regular graphs, but simple stage to say it's geometry. So that's the constructions. Now, one consequence of this, of course, is that our field must have prime power order, and so we can get Q plus 1 mutually unbiased bases in C to the Q when Q is a prime power. Okay. So, well, first question I'm going to turn to, though, is simply that how large can a set of mutually unbiased bases be? And I think I've got the time. I might just cut to the conclusion here. The maximum size of a set of pairwise mutually unbiased bases in C to D is D plus 1. So the example I just gave, if you work through and do the details, is optimal. Okay, I think I'll just go on to next. So that leaves you with a couple of problems. First, well, as I said, this bound is realized when Q is a prime power. Can it be realized in any other case? Nobody knows. And this has been open in a long time, and people are interested in mutually unbiased bases. As I said, they're used in lots of different protocols. Secondly, if D is congruent to 2 mod 4, no one has found more than 3 mutually unbiased bases. So particularly in D equals 6, you can get a set of lots of ways of getting sets of 3, but no one's ever done any more. The physicists seem fairly confident you can't do better than 3. So there are 2 simple questions. They're simple to ask, I should say. I want to give a slightly different formulation of the problem. I can state this in terms of a calligraph, and this will connect to things I'm talking about later. I'm going to construct a calligraph. The only problem is perhaps that there's going to be an infinite calligraph. The vertices of the D by D unitary matrices. Okay, so I'll tell you what the vertex is. Now the edge set, I'm just going to say the 2 matrices M and N are going to be adjacent if N star M is flat. Now, the set of flat matrices is closed under inverses because the inverse for unity matrix is just the conjugate transpose. So if the matrix is flat, so is its inverse. And it doesn't contain the identity. And so I get a calligraph, a nice proper graph. And so the question we're asking about the first question there is simply asking, what is the maximum size of a clique in that graph? The theorem, which I didn't go through, tells you it's at most D plus 1. And the question is, can you realize D plus 1 if D is not a prime power, for example? Okay, so that's it for lines. The next thing is kind of a transition between the lines and the coloring. Related to something called Gleason's theorem, which was proved in 1957. So this predates quantum computing and all. It's an early result. And well, there's a physics result, but I'm going to say that in purely graph theory terms, but I needed to find one more graph. Again, it's an infinite graph. The vertices are the unit vectors in R to the D, and 2 unit vectors are adjacent if they're orthogonal. So it's a well-defined graph. And a question you could ask, you probably rather not, but you could ask is, what is the chromatic number of this graph? Now, the first thing to realize, of course, that any orthonormal basis in this graph gives you a clique of size D. So there are cliques in there of size D. And it's also easy to see you can't have a clique with more than D vertices because an orthonormal basis is going to have at most D elements. So we get that the D is equal to the clique size omega of S of D. And that's a lower bound in the chromatic number. So I'm going to rephrase my question, revise question simply, is that the chromatic number of D? Now, I first learned this question from Joseph Sachs, who'd been to one of the Southeastern conferences and came back and said that Peter Frankel had asked exactly this question. And so we started looking at it, although what we did then is not what I'm going to talk about today. So the reason, well, what happened is, although this question was asked in the 1990, Gleason had already settled it in 1957, and so I've explained the connection there. So the thing I need to work with is not too unusual. I'm going to call that is a fractional co-clique in a graph. So a fractional co-clique on a graph is a map from the vertices to the non-negative reals, with the property that sum over the vertices of the clique is at most 1. Straightforward enough. And a fractional co-clique is tight if its sum over any clique of maximum size is equal to 1. Now, the only graph I'm going to, apart from 3 examples to help explain the concept, the only graph I'm going to be looking at fractional co-cliques and tight fractional co-cliques is this orthogonality graph. Okay, and so there the maximal cliques have size d, and so I want a function on the elements on the unit vectors that sums to 1 on any orthogonal basis and is non-negative. Okay, and so it's a tight fractional co-clique. Now, a couple of examples. The characteristic function of a co-clique, that's a 0-1 valued function, but it is a fractional co-clique because any co-clique has got at most 1 vertex in any clique. And so the sum condition is satisfied. If you want a tight example, if a graph is connected and bipartite, then a color class is a tight fractional co-clique because the maximal cliques are just the edges, and every edge contains a vertex in each color class. So that's 2 straightforward examples. And so what did Gleason prove? Well, Gleason proved that if the D is at least 3, it's false if D is equal to 2, and F is a tight fractional co-clique. Then there is a density matrix D, a positive matrix trace 1, such that F of X is equal to X transpose DX. Okay, so just think about this. I've defined fractional co-cliques, and that's sort of thing that comes up in combinatorial optimization. There's nothing unusual about it, but and we've defined tight fractional co-cliques, and now we're working with an infinite graph, and now we have this explicit description of the possible fractional co-cliques. So it's really quite remarkable. The physicists complain about this a lot because they say that they talk about having a notoriously difficult proof. It is complicated. I did more or less work through it once. I mean, it would be easy enough to find other proofs in mathematics that are just as complicated. Anyway, there it is. So he proved that if there was a fractional clique, it had this specific form. Now, for the physicists, this was important because it basically justifies us using density matrix to represent states. So from the point of view of foundations of quantum mechanics, it's a very important result. But we're not physicists, we don't care about that. So the comment I want to make is the hard part of the proof of Gleason's theorem was showing that the fact that a tight fractional co-clique is necessarily continuous. So we don't care about this as a form, we just get continuous. Now, the point about that is that tells you that you can't 3-color the unit sphere in 3 dimensions. Okay, because suppose I could 3-color the unit sphere in R3. Okay, then I color them, well, let's say 0, 1, and 2. Let's be lazy, color them as 0, 1, and 2. Now, each clique must get 1 vertex must be labeled 0, 1 vertex must be labeled 1, 1 vertex must be labeled 2. And so if I look at the vertices labeled 0, that will be a fractional co-clique, and it's tight. But Gleason tells us, but that's not a continuous function. So there can't be a 3-coloring of the orthogonal graph in R3 or in any dimension greater than 3. Okay. So as I said, I think it's really quite remarkable that there's a fundamental result in the theory of quantum mechanics. And it's got this translation into questions about colorings. Joseph Dax and I came up with another proof of this that used valuations of field extensions, so it's completely different techniques. The physicists don't talk much about Gleason's theorem these days. They usually refer to what they call the Koch and Specker theorem. From my point of view, well, from any point of view, the Koch and Specker theorem is what you get from the Gleason's theorem by compactness. And so the Koch and Specker theorem is essentially the assertion that you can find a finite set of co-cliques in S to the D, or co-cliques of size D, and that induce a subgraph with a property that doesn't have a tight fractional co-clique, and so therefore its chromatic number is greater than D. Now, if you have an infinite graph with chromatic number greater than D by the de Broglie-Erdos theorem, there are finite subgraphs with chromatic number greater than D, but we're not just asking about chromatic number, we're asking about fractional co-cliques. But compactness gives it to you. And so this gives you the Koch-and-Specker theorem. And most textbooks, or a lot of textbooks on quantum physics will be talking about Koch-and-Specker theorem. Most don't mention the Gleason theorem because of its notoriously difficult proof, I guess. Okay, so I was talking about coloring the sphere in R3. I want to go a little bit further. Now I'm going to talk about coloring and just coloring graphs. Now, well, in fact, I'm going to come up with a different type of coloring, quantum coloring, and so it'll take me a little while to set that up. So first I need to, basically what I'm going to do is come up with a much more complicated way of defining chromatic number, but let's not get ahead of myself. So a homomorphism between two graphs is a map from the vertices of one to the vertices of the other, such that if U and V are adjacent in X, then their images are adjacent in Y. And for your amusement is one very simple example. Phi cycle mapping on the K3 with an edge. So that's an example of homomorphism. The classical example, of course, is that a graph has a homomorphism to KR, if only if it's KR colorable. And another classic example is any isomorphism between graphs is a homomorphism. Okay. So so we normally define the chromatic number of a graph by saying the graph is n colorable if it has a homomorphism to Kn. Actually, we don't normally define that, but we could define that way. It's not too big a stretch. I'm going to introduce a more complicated graph, the derangement graph. Now, this is a finite graph. Its vertices are the permutations of length n, so the elements symmetric group sim n, and two permutations sigma and tau are adjacent if the tau sigma inverse has no fixed points. Or in combinatoric terms, the permutation tau sigma minus 1 is a derangement, doesn't fix a point. And again, so that's a graph on n factorial vertices. Now, for coloring purposes, the questions are, what are the cliques, what are the co-cliques, what is the chromatic number? Well, it's easy to see that here, for example, I've given you those four permutations form a clique of size 4 in the derangement graph D of 4. And those set of four permutations form a Latin square. And if you think about it for a few minutes, you'll realize, of course, that a set of permutations forms a set of D permutations length D forms a clique in the derangement graph if only if it gives you a Latin square. So Latin squares corresponding cliques, and so the size of the largest clique in the derangement graph is n, and they're all realized by Latin squares. Now the co-cliques, you want two vertices. If you take the permutations that fix 1, then sigma tau inverse always fixes 1. Okay, and more generally, if you take the permutations that map I to J, they form a co-clique. And that forms a co-clique of size n minus 1 factorial. And in particular, the cosets of the stabilizer of 1, say, form a partition of the derangement graph into co-cliques of size n minus 1 factorial. And so you see that the chromatic number of the derangement graph is n factorial, is n. Okay, and so now I can have my complicated definition saying that the graph is n colorable if and only if it emits a homomorphism into the derangement graph on n vertices. Okay, so that kind of justifies what comes next. There's a quantum version. To that, I have to replace the symmetric group by the unitary group. And I define a unitary derangement to be a unitary matrix with 0 diagonal. Now, a permutation, if you write your permutation as an m by n matrix, then it's a derangement if only if it's diagonal at 0. So the unitary derangements contain, in special cases, the ordinary permutation derangements. And in analog to the derangement graph, I'm going to define the unitary derangement graph. The vertices are now the elements of the unitary group, and the m and n are adjacent if n inverse m is a unitary derangement, so that the diagonal entries of n inverse m are all 0. Now, the set of unity, if you've got unitary matrices with diagonal 0, then the inverses have diagonal 0, and the identity matrix doesn't have any 0 entries on the diagonal. So the set of I get a Cayley graph, okay, from this description. The connection set is just the set of derangements. So I've got a unitary analog of my derangement graph defined using a symmetric group. Now, I didn't make this up. The definition, one definition is a graph has a quantum n coloring if it emits a homomorphism into the unitary derangement graph. So we can define ordinary n colorings in terms of homomorphisms into the derangement graph. We get quantum n colorings by homomorphisms into the unitary derangement graph. And the comment is that since the ordinary derangement graph is a subgraph of the unitary derangement graph, the elements are sim-endless matrices, you see that the quantum number is bounded above by the classical covariant number. Now, I should say what I'm giving you is a somewhat simplified. The official definition of quantum coloring is more complicated than what I've given you, but this has been used, and so it's a good place to start. So I won't say anything more about that. Now, sorry, again. You won't worry about clicks in the graph. I just want to so yeah, let's go straight to here. So I've now got two parameters. I've got the chromatic number and the quantum chromatic number. And so of course we expect that these should be different in some cases. And so I'm now going to outline proof for just how different they are. Now, to do that, I need to introduce yet another infinite graph. I'm going to call it Sflat, which its vertices are the flat unit vectors in C to the D. So, okay, so unit vectors with all entries equal and sum of the squared equal to 1. Now, so it's a subgraph of the unit vector graph in C to the D, although before, when I talk about Gleason's theorem, I was working over the reals, but now I'm working over the complexes. Now, just as a bit of notation, I'm going to use delta sub Z to denote the diagonal version of a vector Z. Now, if the vector Z is flat, then delta sub Z is a unitary matrix. Yeah, think about it for a second, but it's a unitary matrix. It's not the most complicated unitary matrix, the unitary matrix. And I want to construct a homomorphism from S-flat into the unitary derangement graph. And to do that, I need to pick some D by D flat unitary W, and I don't care what it is. So you can take it to be the character table of your favorite abelian group of order D, for example. And then, okay, so got my flat unitary W, and then the observation is that delta Z W is unitary because it's a product of unitary matrices. And there's a nice little calculation required, which I'm not going to give you, but you can check that. So what I'm looking at here is the unit product of delta ZW with delta YW. We're looking at the diagonal entries of that product. Okay, diagonal entries of this product. And it's actually, the diagonal entries are all equal to the inner product of Y and Z. And so the map that takes Z to delta ZW is a homomorphism from S-flat to the derangement graph. So the derangement graph sits inside the unitary, sorry, the flat orthogonality graph sits inside the unitary derangement graph. Okay, so now I want to consider a natural enough graph. And this one's finite. The vertices of plus or minus 1 vectors of length D, and the edges are to such vectors are adjacent if they're orthogonal. Franklin-Rödel proves if D is odd, this graph has got no edges. If D is even, it's bipartite. So then interesting cases when 4 divides D, and in a deep paper by Franklin-Rödel, actually quite a bit harder than the paper by Gleason's result, they proved that the chromatic number of this graph, the orthogonal graph on plus minus 1 vectors, is of order C to the D, where C is some real number greater than 1. So that tells us that the chromatic number of this omega D grows exponentially with D, but omega D is a subgraph of S-flat in D dimensions, and that has a homomorphism into the unitary derangement graph, and so the quantum chromatic number of omega D is just D. So there's not just that the quantum chromatic number is not doesn't always coincide with the classical chromatic number. There can be a huge difference. Now, I think now I can spare you that. I just wanted to finish off with, well, something since I've worked in algebraic graph theory. There's lots of interesting eigenvalue bounds on parameters related to coloring. So bounds on size of cliques, bounds on size of co-cliques, bounds on chromatic number. And one of the oldest and most famous is Hoffmans Bound, which says you've got a k-regular graph with least eigenvalue tau. The chromatic number is at least 1 minus k over tau. Now tau is negative, so it's fine. Now the interesting thing, I think is really interesting, is that Elvig and Watson proved that 1 minus k on tau is actually a lower bound on the quantichromatic number. And this is not an accident. There are a number of classical parameters on these things, like size of co-cliques, size of cliques, and many of them the bounds turn out to be not just a bound on the classical parameter, but on a natural quantum analog. And it seems a bit unreasonable to me that we have these. We knew that these Hoffman bound is not always tight, but one reason it's not always tight because it's not really just a bound. It's not really a bound on the chromatic number. It's really a bound on the quantichromatic number. That could be different. And so I'll stop there. Thanks for your attention.
Thanks a lot for your very nice talk. So now we have some time for questions. So if you have a question for Professor Godsil, please type it in the chat. Or if you want, you can put your hand up and request to be unmuted and ask with your voice. So I'll wait for some questions to come in and I can read them out. In the meantime, here's a question for you. So can I ask, Gleason's theorem goes back to the 1950 something, I think. Do you know what the motivation was for him to work on that problem?
It was exactly, he was concerned with the interpretations of quantum mechanics, and basically it was justifying the use of using density matrices to represent states. So in a sense, it said that if you had some natural concept of measurement on natural states, then you had to do it using density matrices. Now, this is a very rough statement, but that was, I mean, the Wikipedia article gives a fair bit of detail on this, for example. But there was von Neumann had given some sort of, attempted to provide some sort of justification. It was von Neumann introduced density matrices things. And according to the Wikipedia article, Bell said he was referred to it as not only wrong, but stupid. He attempts to justify it. But Gleason settled the matter by showing that if you had some natural, given natural conditions, you were going to be forced to, you could do everything with density matrices.
Okay, I see. Thanks.
Yeah.
Okay, there says one hand up, I think, somewhere. So let me. Oh, Changyao, yeah, go ahead.
It's me. Okay. Hi. I have a questions about the uniform missing.
Yes.
Like, what are the existing results on Cayley graphs? Presumably, these are the likely candidates. So, are there any results on Cayley graphs on symmetric group, non-abelian groups?
There is a paper on one class of Cayley graphs, a symmetric group, which proves you don't get uniform mixing. The point is that, well, my student Natalie Mullen wrote a PhD thesis on this, and some of the stuff I was quoting there come from that. And now in the slides for this talk at the end, I've got a bunch of references, and I can make the slides available. And so then some references will be there, and they'll serve as a starting point. The key observation is that you don't, transit is not enough. You don't get uniform mixing on complete graph on KN vertices. In fact, what happens on a complete graph is quite interesting. You look at the continuous quantum walk on the complete graph. You start on vertex 1 for argument's sake, state 1, and you look at a time t. What vertex you like to be on? You'll be on your initial vertex with probably 1 minus a constant over n. So in other words, you with high probability, when you measure, you'll discover that you're on the vertex you started on. That's why we said that there was uniform mixing on K3 and K4, but there's no uniform mixing on K5 or higher. So transitivity is not enough. Now, Natley conjectured that if n was big at 5 or more, then Zn to the D did not admit uniform mixing. So in other words, it's not enough to be, I mean, transitivity is surely a help, but you need something else.
So for...
Yeah, I should also say, sorry, there's some fairly heavy machinery going into some of these things. I mean, she was using algebraic geometry and Goldfein-Schneider theorem and things like this. So
it's not.
Sorry, you can ask.
Yeah, it's not just the spread of the eigenvalues that gives sufficient conditions for uniform mixing.
It's hard to say.
Okay, so I'm just wondering what are the difficulties in getting in the calculations, for example.
Well, one problem when we're working with the perfect state transfer questions, we know that if it happens by a certain time. And so we can look at examples and very quickly get some intuition as to where we should be looking. So the first problem in dealing with uniform mixing is that in general, we do not, for non-bipartite graphs, we don't have any estimate in time. So we don't know at what time it happens. Now, the waiting time could get large. So for example, I was talking about perfect state transfer. When you realize that perfect state transfer is rare, but then you realize that we're working in the real world, we can afford a bit of slop. So let's say we'll have pretty good state transfer. So the aim is that we can get transferred to within accuracy 1 minus epsilon. Well, yes, you can do it. If you do it on pars, you can arrange this, provided the path of length n, provided n+1 is a prime or twice a prime or a power of 2. And even if it does happen, your waiting time is going to be exponential. So, the time at which it happens, you may have an interesting property occurring, but it could be after a very long wait, after a physically unreasonable waiting time.
Thanks, Chris.
You're welcome.
Okay, there's also a question from Bernhard. Please, Bernhard, go ahead.
Okay, can you hear me?
Yes.
This construction of mutually unbiased basis in a complex space of dimension D works very well when D is a prime power. So do you think there is a chance to modify this idea, so to use characters of abelian groups in case where D is not a prime power?
There's no evidence. I mean, it's very natural. There's a lot of people have thought about this. And no one has made any progress. And so at the moment, there's no evidence to believe that if Q is not a prime, there's no reason to believe, according to the evidence I see, that if Q is not a prime power, there will be a set of Q+1 nuclear unbiased bases. I don't know if anybody's actually made it explicitly as a conjecture, but it's probably would be some justification.
Thank you.
Okay, there's also a question from Han Mao. Please go ahead. You're currently muted.
Okay, sorry again. Yeah, good evening. Yeah, good evening, Professor. I'm curious about the chromatic number. Yeah, the Hoffman bound. Okay. Okay. So there's Hoffman bound is quite related to the theta number. So I'm curious if the Gauge theta number. Yeah. How does the quantum coloring bound compare with the Gauge theta number?
Well, as I said, there are there's actually a fairly large number of quantum analogues, and the lowest theta fits between chi and chi q, if my memory serves me correctly. So the real thing is it is known. Okay. In this context, I think it's better to think of lowest theta as the so-called vector chromatic number. But there are a lot of sort of relaxations of quantum coloring and things, and so the relations there are known.
I see.
And so there are papers by Dave Roberson. Now, as I said in the references, I added some references, and they're not exhaustive or representative even, but they give you starting points.
Okay.
For their papers by Dave Roberson.
Okay.
Yeah.
See. Yeah. Okay. Understand. I see. So generally, when will this be, the quantum coloring number be typed? Yeah, intuitively.
Yes, that's a very nice question. Yep. The smallest example where there's a difference is currently on 14 vertices.
I see.
And David and Laura state that I think that might be the smallest. You can take, I don't know, I'd place much weight on that, but I mean, it probably can't be too much smaller. They're not easy to find. I mean, some funny things happen. For example, what came out of this, I had an example of a graph where if you take the cone of that graph, you add a new vertex adjacent to everything, that increases the chromatic number by 1, of course. But it does, in this particular case, it did not change the quantum chromatic number.
I see. Okay.
So some funny things can happen.
Okay. All right. I'll look into it. Okay. Thank you very much. And very nice talk.
Okay, there's a question in the chat. Can you see that, or shall I read it out?
Yeah. Well, okay. I'll give you the long story. So I was trying to decide what I want to do when I went to university. And in a certain sense, my interests and my skills were in mathematics. But it turned out, well, I couldn't have gone to university without getting some sort of scholarship. There wasn't much in the way of scholarships available. But I did get a kind of a scholarship to work with this what was called the Commonwealth Serum Laboratories, a biochemical company, and so they gave me an arrangement. They paid me through university, and I worked there over the breaks, and then I had to work for them for 4 years after I graduated in biochemistry. Basically, they really needed engineers, but biochemists were cheaper to pay than engineers. So I worked there 4 years. I mean, it was obvious more or less from the start that I'm better off in mathematics than biology. I still remember the biology lectures in first year. The lecturer would come in with 3 or 4 pages of closely handwritten material and start to dictate it. And he could dictate faster than I could write. But anyway, so, I sort of realized I wanted, and so while I was at university, I took some math course. And so I realized that was, in some sense, what I was most interested in. So then I started taking some math courses while I was working as a biochemist. And then when my 4 years were up, I went back and I had to do the 4th year of the so-called honours year at the University of Melbourne, and then went into the start on a master's degree.
Okay, so I think that's all we have time for. Thanks everyone for asking a question, and thanks a lot to Professor Godsil for giving a very nice talk. That concludes today's session. Thanks a lot for attending, and see you next time.
Thanks, Gary. Thanks, guys.
Thanks a lot.
Thanks, Chris.
Thank you.